In today's lesson on exponential and logistic modeling, our goals are to write an exponential growth or decay model, f of x equals a times b to the x, and use it to answer questions in context. We will use an exponential growth factor, which is b equals 1 plus the percent rate as a decimal, and exponential decay factor, where b equals 1 minus the percent rate as a decimal. And we will write a logistic growth function given the y-intercept, both horizontal asymptotes, and another point. Let's look at our first example. The population of Glenbrook in the year 1910 was 4,200. Assume the population increased at a rate of 2.25% per year. Growth rate is b, which equals 1 plus the percent rate. Here our percent rate is 2.25%. So our growth rate is 1.0225, which was our 1 plus our percent rate of 0.0225. Our initial population is 4,200 people. This will be our A value. If we let x equal the number of years since 1910, we can build the equation of the population growth. So we'll have f of x equals our initial population of 4,200 times our b, which is our growth rate, 1.0225, raised to the x. Here, f of x will be our population. So next we want to determine the population in 1930 and 1900. We must figure out what x is. In 1930 is 20 years after 1910, which is what our initial x was. So 1930, our x would be 20. So to find out the population in 1930, we'll do f of 20, which equals 4,200 times 1.0225 raised to the 20. And when you evaluate this, you're going to get a population of 6,554 people. Now for 1900, this is 10 years before our start. So our x is going to be negative 10. So f of negative 10 equals 4,200 times 1.0225 raised to the negative 10. And when we evaluate this, we get a population of 3,362 people. Now, we want to determine when our population is double the original amount. So that means we must find x when f of x equals 8,400. So we'll have 8,400 equals 4,200 times 1.0225 raised to the x. So to solve for x, it'll be best to put this in our calculator. So we're going to have our y equals 1, our y1 equals 8,400, our y2 will be 4,200 times 1.0225 raised to the x. We'll set our window so we can see it. So minimum of 0 years, maximum of 80 years. We scale a little bit bigger. And our population, we want to find out when it's 8,400 people. So we'll go all the way up to 9,000. So what we're going to do is we're going to calculate the intersection of these two lines, and that'll give us our x value. So our intersection here is at a value of 31.15. So here x equals 31.15 years. This means that the population will be doubled 31.15 years after 1910. So 1910 plus 31.15 years equals 1941.15. So in the year 1941, the population will be double its original amount. Now let's look at another common application. Half-life. This is an example of exponential decay. So to figure out where we're going to start, we're going to define our variables. We're going to let x equal time in days, and we're going to let f of x equal our mass in grams. That's remaining. So we know that half-life means 50% of the original amount has decayed, so our rate is b minus, which is b 1 minus 0.5. And we'll be left with 1/2, or 0.5. And it decays this much every 14 days. So we're going to have our function of f of x equals our initial 10 grams present times our decay rate, which was 1/2, raised to the x, but we have to take into account that the decay rate is every 14 days. So it'll be x over 14. So now we want to know when there is less than 1 gram remaining. So we're going to have to use an inequality to solve this. So we'll set our function 1 less than our function. So we'll have 1 that's less than 10 times 1/2 raised to the x over 14. And again, this one would be best to solve by putting in the calculator. So we're going to have 1, and on the other side we'll have 10 times 1/2 raised to the x divided by 14. We'll set our window, the 0 to 80 is pretty good. And we'll go from a y minimum of 0 and a maximum of 2, since we're trying to figure out when it'll be less than 1. So now we're going to calculate the intersection. And we find we get an x value of 46.507. So x equals 46.507. Now we want to know when our substance has less than 1 gram remaining. So that's going to be this area over here. So we know that we'll have less than 1 gram remaining when x is greater than 46.5. So this means there will be less than 1 gram remaining after 46.507 days. Now for our last example, we need to find a logistic growth function with a y-intercept of 5 that goes through the point 24, 135. Remember, c is our limit of growth, and here we can see that it is 500. So we can start by building our equation. Our equation so far, using our limit of growth of 500, is 500 all over 1 plus AE raised to the negative BX. So now let's use our y-intercept of 0, 5. So we'll put 5 in for y and 0 in for x. And we'll be left with 5 equals 500 over 1 plus a multiplied over, divide by 5, and we'll be left with a equals 99 after we subtract our 1. So now our equation looks like y equals 500 all over 1 plus 99 e to the negative bx. So now we're going to use our point 24, 135 to solve for our b value. So we'll plug in 135 for y and 24 for our x. And then we're going to multiply over, divide by 135, and here it'll be best to use the calculator to determine what our x value is. So we're going to put in 1 plus 99 times e raised to the negative 24x, and then the other side of our equation is 500 divided by 135. So we're going to make our window a little bit larger. Our x max is going to be pretty small, but our y maximum is going to be a lot larger. That didn't work too well. Change the y max to, say, 50. That gives us a better graph there. And we can see that intersection, so we're going to calculate. And we have an x equals 0.1500. So our x, or in this case our b, is going to be 0.15. So our final equation is y equals 500 all over 1 plus 99 e raised to the negative 0.15x. You must leave the negative there because it's in the beginning. We just solved for b itself. And that is it.